Moving on to Anne Jimenez from Mango Materials. This is another one of our wonderful companies that we've worked with very closely. A company that transforms biogas into biodegradable, functionally competitive bioplastics. Anne.
Thank you. I'm here today to tell you how my company can solve two environmental issues. The first is plastics. They're all around us. But do we always think about where they came from and what happens to them when they're no longer needed? The second is that of methane, a greenhouse gas that's generated from wastewater treatment plants, landfills, and agricultural facilities. And while methane can be collected, it is often underutilized and therefore flared into the environment, such as the photo that I'm showing here. So what do plastics and methane have in common? Well, my name is Anne Schauer Jimenez, and I'm VP of Methane Marketing and co-founder of Mango Materials, where we turn this waste methane into eco-friendly, affordable plastics while creating a positive environmental impact. And here's how we do it. We take the methane and feed it to our specialized set of microorganisms who convert the carbon into a long-chain biopolymer. This biopolymer is very versatile and can be converted into many different products. And when these products are no longer needed, they could end up back at a waste facility. But if they're degraded anaerobically without oxygen, methane is generated, closing the loop and creating a cradle-to-cradle process. The type of plastic that we make is called polyhydroxyalkanoate, or I'll call it PHA from here on out. And our methanotrophs, our bacteria, actually do something pretty interesting. They naturally make this plastic inside of themselves. So these white inclusions that I'm showing here is actually the plastic. So we do have to break open the cell and separate the plastic from the cell material. Ultimately, we would sell the plastic in a powder or a pellet form. PHA is really interesting in the fact that it has a lot of unique end-of-life characteristics. For instance, it can be fully biodegradable in your home compost, or in a modern landfill, or in an anaerobic digestion system at a wastewater treatment plant or an agricultural facility. But it's also degradable in the aquatic environments, such as the oceans. And it's because of these unique properties that Mango Materials is really interested in applications where end-of-life and biodegradability is key. So marine buoys or fishing lures, or in the agricultural sector where we could make agricultural films that could cover the crops during the growing season. But once the crop is harvested, it can be tilled into the soil, and instead of creating contamination, can actually be degraded by the soil microorganisms. We're also interested in applications for 3D printing, for additive manufacturing, which actually generates quite a bit of waste. Mango Materials was spun out of Stanford University, where our CEO, Molly Morse, and our CTO, Allison Pija, did their PhDs. We incorporated the company in 2010 when I joined, and we own exclusive licensing to all of the IP of the methane to bioplastic technology that Molly and Allison did at Stanford. We are now up to 15 full-time technical employees, and we have a handful of part-time help in the areas of business, legislation, and project management. We also have two partnerships that have been key to our success. The first is the USDA Agricultural Research Service in Albany, California, where we do our small-scale optimization and polymer characterization. The second is Silicon Valley Clean Water, a wastewater treatment plant in the San Francisco Bay Area. We're currently focused on scaling our technology, and we're optimizing our demo unit at Silicon Valley Clean Water, where we can take their unscrubbed biogas to produce customer samples of our PHA biopolymer. But we don't want to stop there. Our goal is to build our Mango Standard facilities. These are our full-scale commercial facilities that will be co-located at the site of methane production. We envision that these Mango Standards could come in 3 sizes, cleverly named small, medium, and large. The small facility can produce upwards of 2 million pounds of PHA per year, and the large up to 30 million pounds of PHA. And this is dependent on the methane flow and the sizing of the equipment. We anticipate our first Mango Standard facility to be built within the next 2 years. So generally, where there's people, there's methane. But also, where there's farms, there's methane. And if we collected all of the methane from US dairy farms and converted it into bioplastic, we could produce 3 billion pounds per year. Currently, PHAs are selling for anywhere from $3 to $20 per pound on the market. But using methane as a feedstock, we can drop that price to $1 a pound, making it competitive with petrochemical-based plastics. Also, we've done some economic analysis that has shown that it's 5 times more economically favorable to convert the biogas to bioplastics versus more traditional uses, such as electricity. So here at the showcase, we're looking for partnerships in the methane space, where we would ultimately be purchasing the methane and need things like square footage and water and utilities for our Mango Standard facilities. But we're also looking for partnerships in the plastic space for the various different applications. And we're currently raising money, most specifically patient capital, so we can build our Mango Beta facility, which is our next scale up, and then ultimately our Mango Standard facilities. Because at Mango Materials, we believe that a closed-loop plastic economy is now possible. So let's build it. Thank you.
Very nice. Questions? Yes, sir.
So I understand correctly that your plastic produces methane upon degradation?
Correct.
Methane is 25 more powerful greenhouse gas than carbon dioxide. So how could you clarify how it's going to be ecologically beneficial?
Oh, well, if it goes back into the facilities that degrade, like an anaerobic digester, then it can be collected again to make more plastic, closing the loop instead of having it emitted into the atmosphere.
So you have to collect it to a special facility rather than send it to waste?
If it's at a landfill, there could be a bioplastics production plant there, or even if there's one for electricity. So if there's a facility that's producing electricity on site as well. So we're basically like sequestering the methane for a temporary use instead of flaring it into the atmosphere.
To basically reduce the greenhouse gas emissions by sequestering the methane, I guess is what you're saying, right, Anne? Questions? Thank you so much. Appreciate it.
Thank you.